Então, na verdade, não tem deixa eu desligar o microfone. Não tem uma área que eu preciso ficar, né? Na verdade, eu só mais ou menos aqui.
Hello, everyone. Good afternoon. Now we have the talk of Professor Raul Teixeira. Raul did his doctorate in France at Université Marie Curie in the group of Professor Sérgio Arroche. He did his postdoc here at the Institute of Physics in São Carlos, USP, in the group of Professor Philippe Coutrel. Since 2016, he is professor in the Department of Physics at the Federal University of São Carlos. He has experience in atomic and molecular physics, working with cold atoms, Bose-Einstein condensates, and Hilbert atoms. His main lines of research include the study of radiation-matter interaction in light scattering by dense atomic samples, microwave atomic spectroscopy, and many-body system. Thank you, Raul, for accepting our invitation. I think you can start.
Thank you, Monica. So, okay, are you listening to me? It's fine? Okay. Mais alto? Is this better? Okay. So thank you for the invitation, Monica, for this really nice school. So in this talk, I have 1 hour to try to talk about the really broad subject, which is the interaction between light and atoms. So this topic is broad and has lots of applications and lots of different topics being studied inside this topic. I have chosen to do something basic, a little basic, since this is a school, but I want to reach the physics that we want to do in our laboratory, okay? So I hope, so of course things are going to be rather qualitative sometimes. I have done a mostly qualitative talk. I hope some ideas will be clear for you, and not the details, technical details about the ideas, but the ideas themselves, okay? If you have any questions, even technical questions, you can ask me, and I can explain or try to explain. But in principle, will be a little more qualitative, okay? Very well. So, this talk has 2 main parts. In the first part, I'm going to put our atoms, which I call quantum dipoles, because I'm going to treat them as a dipole in quantum mechanics, so a dipole that can be excited by light. So I'm going to put these quantum dipoles first in free space, so they are going to interact with light in free space, and then we're going to put them inside a cavity. Both things are studied by lots of groups, and in particular by our group here at Instituto de Física de São Carlos. So, what's a quantum dipole? I think everyone knows this already after these 2 weeks of school and after everything you have seen in physics in your life. So I can characterize a quantum dipole as an atomic as a transition, a quantum transition between 2 levels. So I show here the ground level and the excited level. Okay, I can point. Do they have a pointer? Here. Is this a pointer? Okay, I'm sorry. Okay, so it seems that I need to use the mouse. Okay, so I can use it here. So let's imagine I have a ground level and excited level. So I can talk about omega 0 is the natural frequency of the transition. So this is proportional to the energy difference between the 2 levels. And gamma, what I call gamma, is the natural line width of the transition. Okay, so gamma is the width in frequency of this transition and is also the decay rate of the excited state back to the fundamental state. So when I am in the excited state, after some time I decay and I emit a photon, and this decay rate is given by gamma. Now, I treat my atom as this simplified 2-level system because I'm going to send on it light almost resonant with this transition. So I don't need to consider other levels. So now I send light. So you should imagine now that you have your atom and I'm sending light on this atom. The light I send has a frequency which is omega L, which is close to resonance with the transition of the atom. So the detuning is delta. And this light couples to my transition with a coupling frequency which is called the Rabi frequency omega, which is proportional to the dipole moment of this transition and to the electric field of my light. Okay, So when I say that the Rabi frequency measures the coupling of my light and my atom, what does it mean? So if the coupling is strong, this means that I am exciting this transition with big probability. If the coupling is small, the probability is small. Two plots show this here. So in the first plot, here in the left, I am showing the probability of having my atom excited in resonance, so detuning equal to 0 as a function of the saturation parameter. So the saturation parameter is here, is just proportional to the ratio between the Rabi frequency and the gamma to the square. So if the saturation parameter is smaller than 1, this means that the Rabi frequency, the coupling parameter, is smaller than gamma, and we are in this linear regime. The probability of excitation is small, and the excitation grows linearly with the saturation parameter. Okay? So saturation parameter is just proportional to the intensity of light, because it's proportional to the square of the electric field of light. Now, if I increase my saturation parameter, I couple strongly to my atom, and I saturate. I cannot have a population in the excited state of more than 1/2. This is a maximum allowed for a two-level system, and I saturate it. This means that I'm strongly coupled to my atom. I can see also this strong coupling in the spectrum of my excitation. If my saturation parameter, the coupling to my atom is small, I have probability of transition probability as a function of detuning that makes a typical Lorentzian profile with gamma. And if I saturate my transition, I send lots of intensity, light intensity. I broaden my transition, and the width becomes actually omega, this Rabi frequency here, okay? So this is just for one atom. This is a really simplified picture. Actually, in reality, we have a picture which is a little different from this, because light is not a scalar wave, light is a vectorial wave, so light has polarization. And each polarization of light can excite a different transition from my atom, okay? So if I send light, a photon with angular momentum, the atom will absorb this angular momentum. This means that light can only excite a transition from between levels with different angular momentum. So the simplest possible transition is a transition from a level with j equal to 0 to a level with j equal to 1. So total angular momentum 0 to total angular momentum 1. And then depending on the polarization of my light, I can excite a sigma minus, sigma plus transition. Okay, so this is the basics. I think most of you already knew about that. This is for only one atom. So just to give some more intuition about that, these atomic transitions are narrow. You see that if I take a typical D2 line for rubidium, gamma is equal to 6 megahertz, the width of the transition. And if I compare this to the natural frequency, which is 284 terahertz, I see that this ratio is equal to 10 to the minus 8. So we are talking about a resonator which has a really narrow resonance, okay? And it can be even narrower. If I take strontium atoms, for example, I have available broad transitions of 30 megahertz, but I have transitions of width 7.4 kilohertz, which makes gamma divided by omega 0 equal to the 10 to the minus 11. And actually I have even narrower transitions. I have transitions which make millihertz width in strontium. So we are going to discuss why this is possible for strontium in a while. But now we see that any of these transitions are all narrow for an atom is isolated in the environment and well controlled. Okay, they are all narrow. And also, from the point of view of the possible transitions the photon can make, often they are more complicated. So if I take rubidium, for example, I don't have a simple j equal to 0 to j equal to 1 transition. I have transitions from states of angular momentum 1 or 2 to states of angular momentum 0, 1, 2, or 3. So if I take the transition from f equal to 1 to f equal to 2, for example, I have lots of possible transitions, which complicate my life if I want to study the interaction between light and matter, okay? Complicate a little things. Again, for strontium, those transitions are simpler. So you see that I am advertising strontium. This is because we do strontium, but actually it's the opposite, is the other way around. We do strontium because strontium is simple from the point of view of light scattering, okay? So this is just a single atom. Okay, so now, if I put more atoms Actually, I'm going to put several of them together. Is this going to be the same as for one single atom? So a naive approach would be to say there's nothing more in n atoms than I have in one single atom. So if one atom absorbs a certain amount of light, n atoms will absorb n amounts of light. And if one atom emits light with a rate which is given by gamma, n atoms emit light with a rate that is given by gamma also, because they are emitting independently. Is this true? So actually this is not true. Okay, so a cloud, when an atomic cloud is composed of n atoms, you have collective effects that will change this picture, this simple picture. Okay, so here to begin with, let's take a cloud which is dilute. Dilute means that the density is small enough. What is small enough? Small compared to what? So the density here is small compared to k to the cube. You see, so the cloud is dilute. This means that the density n is much smaller than k to the cube, where k is the wave number of the light that I send to be absorbed by my atoms. Okay, so this means that what does this mean? This means that in a cube of side lambda, where lambda is the wavelength of light, I have much less than one atom. So I have much less than one atom per wavelength to the cube. Okay, so this is a dilute cloud for me. So in this dilute cloud, the absorption and emission of light is changed with respect to the single atom, and everything depends on one only parameter, which is the optical depth of my cloud. Okay, apart from the geometry, but if I take only spherical clouds with Gaussian profile, for example, everything depends only on the optical depth of my cloud. What's the optical depth? So the optical depth, I'm just giving here the mathematical expression. But so what's in this expression? Sigma 0 is just the absorption cross-section of my atom, which is like, you can imagine, you can think about the absorption cross-section as the shadow that an atom makes on light. So if you have one atom in a low intensity beam, this atom will remove energy from the beam as if it was a disk of area. Okay, I think it's wrong here. It's not 3 pi divided by 2, it's 3 divided by 2 pi. There is a problem here. Times lambda squared. Okay, so each atom of my cloud is removing light like if it was a disk when the light is on resonance. And in the end, the light that passes through my cloud is attenuated, and this attenuation can be measured by this optical depth. So the Lambert Law will say to us that the intensity after passage is equal to the intensity before passage times e to the minus b0. All days for low intensity light. If my light is saturating my atoms, it's a completely different story. But for low intensity, this is what happens. Okay? So this is Lambert Law. And so you see that the absorption depends only on this optical depth. Now, this absorbed light needs to be emitted somehow. Okay? And this emission is also not going to be as the emission of the individual, the independent atoms. This emission will suffer from collective effects. Okay? So when this, let's imagine that I'm sending light to my atoms and then I cut out the light. When I cut the light, the light that is stored on my cloud will begin to escape, and this light escaping, it will not escape necessarily with a rate equal to gamma, as it was the case for independent atoms. The rate can be higher or lower, and this is called superradiance or subradiance. Okay? And I can also have a shift of my transition due to the presence of the other atoms. Okay? So why this happens? Why the emission of n atoms is not anymore equal to the emission of only one atom? Okay, and I can also have radiation trapping because you have multiple scattering, but this is linked to superradiance and subradiance, and I'm gonna focus on these changes in the light emission now, superradiance and subradiance. Okay, and also what's important here is that everything scales with the optical density. So superradiant behavior, superradiance and subradiance can be understood if I think about this cloud, now if I think about what happens when these atoms emit light. So when I have one atom that is in the excited state, why does this atom decay? So this atom decays because the dipolar transition of this atom is coupled to the vacuum quantized electromagnetic modes of the radiation, okay? So if there was no vacuum modes, this atom would continue to be excited forever. But since there's a coupling between this dipole and the vacuum modes of radiation, this coupling makes this excitation eventually escape through these modes. And so this excitation becomes a photon that goes away. Now, these N atoms are all coupled also to these modes, okay? But this coupling, but now when I write the coupling between each one of those atoms and the vacuum modes, I see that actually more than one atom can be coupled to the same mode. And this makes, if I take a look now about this coupling between each atom and the modes, I see that I can have one atom coupled to one mode, and this mode coupled again to another atom. So one atom can emit one photon, and this photon can be absorbed by another atom. So this makes an effective coupling between the atoms. And now the interaction between these, which makes that the emission of one atom is coupled to the emission of the other atoms. So I do not emit independently anymore. And if I diagonalize this coupling, if I write the matrix of the effective coupling between all those atoms, I see that I end up with modes. And now this cloud interacts with light via normal modes, which are not equal to the independent interaction of each atom with these vacuum modes anymore. So these modes has decay rates now that can be bigger than gamma or smaller than gamma. So every mode that has a decay rate bigger than gamma are called superradiant mode. Okay, so this is a superradiant mode. What's superradiance in this context? Is a decay of the excitation which is faster than gamma. So it does not mean that I emit more light, but it means that I emit this light faster. Okay, so this is superradiance. And I also have modes that emit slower, which are called subradiant modes. Now, I'm showing here the typical decay of the light stored in a cloud of optical depth equal to 15. Okay, so this is a simulation extracted from this article here. If the cloud would behave as independent atoms, I would have that this decay would follow this simple curve here, the dotted curve, okay, which is a curve which is linear in this log link because it's an exponential, so it's linear in a log link graphic. And so this curve is the curve for independent atoms. But I see that actually they follow the blue curve here, okay? So there's lots of different curves here, but we see more the blue. So they follow instead the blue curve. So this blue curve decays first in a faster way. Why do I see this? Because I first see the emission of the modes which decay faster. These modes are the superradiant modes. And then I see the decay of the modes that decay in a slower way, okay? So which are the subradiant modes. So I see that when I excite my atoms, I excite all those modes. And then when I see the decay, I see that the rate of decay changes. I see first the decay of the superradiant modes and then the decay of the subradiant modes, okay? Very well. So this is interesting for quantum resources. Why is this interesting for quantum resources? Because if I have now the behavior of a cloud changing with the number of atoms, the behavior of the interaction between light and matter changing with when I put more atoms, this means that, for example, I could, if I use the superradiant modes of my cloud, I could couple light better to my cloud and I could recover light faster also. Why I could couple light better? Because this goes in the two directions. If my cloud is better coupled, if my mode is better coupled to the environment in order to extract the photon, it's also better coupled to the environment in order to get the photon, okay? So by using superradiant modes, I could input and output photons quicker. And by using subradiant modes, I could store those photons for a longer time. So this could be used. This is interesting, okay? But actually, okay, so this is just the same information, but actually, as we are discussing here, it's not that easy to use those modes because we are discussing those modes in the context of a randomly distribution cloud, and if I produce a randomly distributed cloud, the modes are also randomly distributed, so I cannot know for the cloud I have produced in my laboratory how will I be able to excite a superradiant mode, or how will I be able to store in a superradiant mode, because I don't know how these modes are, because every time I produce a cloud, the atoms are in a random position, okay? So this is not really useful in this state. So it's an interesting phenomena, but not useful for random clouds, okay? So on the other hand, superradiance and subradiance are much more useful for ordered clouds. So if I go to an ordered cloud, I can calculate how are those modes, the superradiant and subradiant modes, and I can use it, okay? Now, I have some slides about the ordered clouds and how to use this, but I will not talk about them right now because I don't know if I have time, so I move on, and then eventually I come back if there is interest or if I have time, okay? So I'll not talk about this. For now, just keep in mind that we have identified that a dilute cloud will emit in a collective way, emit light in a collective way, okay? Okay, so everything that I said is about dilute samples. Now, if I go to dense atomic samples, if I pack my atoms in a way up to the point where I have more than one atom per cubic wavelength in a cubic wave in a volume which is the wavelength to the cube, this means that B0 is not the only parameter anymore. So I have we are going to have another, we will need another scaling parameter in order to describe what's going to happen to the absorption and emission of light, okay? So this parameter I'm going to use, for this parameter I'm going to use the normalized density. So the density of the cloud divided by the wave number of light to the cube, okay? So this determines how many atoms per cubic wavelength I have, roughly, up to a factor 2 pi to the cube, but this is proportional to that, okay? So now things begin to be different when I have a dense sample. Why is this so? So remember that we were discussing about this interaction between atoms mediated by the vacuum modes of light, okay? So if I put something more quantitative about this interaction, if I calculate how this effective interaction is, I discovered that this effective interaction has terms which depend on 1 over Kr, or R is the distance between each one of the two atoms. So this interaction goes like 1 over Kr, 1 over Kr to the square, and 1 over Kr to the cube, okay? And all those terms are multiplied by h bar gamma up to a numerical factor, and all these terms become bigger than h bar gamma when I have R smaller than 1 over K. This means that when I pack my atoms, when they become, the next neighbors become closer than 1 over K, this effective interaction broadens my transition and makes the absorption of light intrinsically collective. So I interact strongly with my close neighbors, and all the characteristics I have shown before are going to change again. Okay? So I don't have just the collective effects due to the coupling, due to the optical depth, but I also have collective effects now due to the presence of nearest neighbors that screw up all my absorption. Okay? So in this context, I have, for example, so I'm going to invert a little here. So in this context, I have, for example, an absorption line which becomes broader and broader and broader as the density increases. So those are simulations that Marcia here did for our experiment, for showing what we expect to measure in our experiment. And we see that the transition not only gets broadened, but also gets additional peaks. It's a little weird, okay? So we still don't fully understand this. These are new results. We don't fully understand why we get 2 peaks. But what we see is that these things are, the absorption gets a completely different profile. So this is completely different from the Beer-Lambert law, okay? So this is completely different. And this has also relation to another fundamental problem, which is the saturation of the refraction index of a medium. So what's the saturation of the refraction index? I'm going to recover your classical electromagnetism courses. And when we discuss in a classical electromagnetism course, why does a material, a dielectric material, have index of refraction? What people say is that, okay, so let's now do a model for matter so we can understand the index of refraction. So what they do is a classical model, okay? So it's an electron connected to the core of the atom through a spring. So this is a classical model. So instead of talking about a quantum transition with natural frequency omega 0, I say the electron is bounded to the nucleus with a spring which has a typical frequency omega 0. Okay. And then we calculate the effect of the light on the atom, and then we can calculate the electric susceptibility of just one atom, and then we can input this in a model to calculate the effect of this matter on the light. So what's the matter gonna make on light? It's gonna absorb light, and it's gonna change the velocity of light inside the medium. So you have a dispersive effect, and you have an absorptive effect, okay? So this is this simple model of the index of refraction. But when we do this in classical electromagnetism, we do the Lorentz model, we calculate the susceptibility, and then we multiply by the density, and we say, so this should be the susceptibility of matter, if matter was to be composed of identical particles. This is really nice. But if we put numbers, if we put the actual numbers that come out of this model, like gamma, everything that comes out of this simple model here, with the frequencies, the natural frequencies omega 0 in the visible region, where the frequencies, natural frequencies of the atoms are, we would end up discovering that the index of refraction should be of the order 10 to the 10. Because actually, a density of eta equal to 1 is enough to make an index of refraction of around 1. And if I put the typical densities, so in a cubic, in a normal solid or normal liquid, in a cubic wavelength of light, I have 10 to the 10 atoms. This would make 10 to the 10 for the index of refraction. And then we never do this calculation. But if we did, the teacher would say, yeah, okay, but see, they interact. So they are not independent. So this is why you don't have an index of refraction of 10 to the 10, because the transitions get broadened. So this simple picture is not anymore true. Well, okay, this is nice. But how do I go from a picture where I have an index of refraction that can be 10 to the 10 to the reality where I never see any material, not even metamaterials fabricated by humans, that have an index of refraction of above 10? I cannot do this. I still have not succeeded. É sim. É. No, desculpa. Okay, so I'm sorry. So index of refraction around 1, I have given no name for the index of refraction. For a density normalized equal to 1. So if this is linear, I should have added this information. This scales linearly. So if I have an eta equal to the 10 to the 10, my index of refraction should be 10 to the 10. Indeed, yeah. I haven't given no name because I had no n anymore, so I was a little... But I should have given another one. Okay. Yes, so this is weird. And a really recent paper from 2020 linked this saturation on the index of refraction to these effects of density on the light absorption. Okay? So if we make a model of independent particles, as I said, as if you had no effective interaction between them mediated by light, you would have an index of refraction that would increase proportionally to density. So you see this here, the index of refraction, the dispersive part is here. So around a transition, I would have an index of refraction that goes really high. These would be the dotted curves here. So they go quite above 1 and 2, etc. already for eta equal to 1, 2, 3. So for the samples which are dense samples when compared to what we can do in the laboratory, but really, really dilute samples when compared to solids or liquids at room temperature, okay? And, but when I include the interactions, I see that this is not the case, that the index of refraction saturates, and also the absorption saturates. The absorption gets broadened and saturates, okay? So the absorption is described by the imaginary part of the index of refraction. Now, if I rescale all of these, if I rescale this axis here by this normalized density, I see that these curves are universal and they all fall into a same simple curve here, okay? From a certain density on. So this is a universal behavior, and this behavior seems to tell us that when I send light, light cannot interact with more than one atom per cubic wavelength. If I put more than one atom, they see each other and the transition gets broadened, and then I cannot talk to more than one. So they exclude each other in this game. Okay? So this is the effects from density. And this problem of light scattering by dense samples is also connected to another fundamental problem, which is Anderson localization of light. Now, to be really, have you heard about Anderson localization here in this school? Okay, so I'm going to be really fast. I just give a simple idea of what's Anderson localization here. So if I talk about scattering of particles, I send a particle to a scattering medium. So what happens is simple. The particle follows a path and goes away. Now, if I send a wave to a scattering medium, so the wave enters with wave vector k and goes out with wave vector k prime. Actually, it's going to go out with lots of wave vector, but let's say I'm observing it in the direction k prime. So the wave can do this first path, but now the wave is going to do all possible paths, because we always talk about the amplitude of scattering for a wave. So a wave can be a little scattered by this atom and then a little by the other one, a little by the other one, so I have a first possible scattering path. But since the wave is arriving on this whole region, I can also have a second path, let's say like this. So the wave can also be scattered by the other atom, the other one, and leaves in the same direction. And all these possible paths are going to add up. And in the end, I need to calculate how the scattered wave is by making the interference of all these possible paths that have different lengths and etc. I also have a path which is as the red, but the small circle that I make there, I do it in the opposite way, for example. Okay, so we have lots of different possible paths. I need to add up all these paths in order to understand the scattering of a wave. Now, when I begin to increase the density of my scattering sample, the sample that's going to scatter my wave, or in the same way, as I begin to reduce the scattering length, which is the average length between two scattering events, so as I reduce the scattering length, I begin reducing the diffusion coefficient from a wave. So here I see the diffusion coefficient D0 if I had no Anderson localization, and as I decrease my scattering length, I decrease the diffusion coefficient, okay? So this is a correction to the diffusion coefficient in first order. And if I continue in this movement, at some point, I don't have diffusion anymore. So my diffusion stops, okay? So why does the diffusion stop? This is because as the scattering length diminishes, the paths where the wave goes to one way or to the other begins to be more and more important. So they begin to appear more and more. And these paths, they interfere constructively because the length is the same. So they interfere always constructively, and this makes the wave to be trapped inside these circle paths, let's say, in a really simple way. So at some point, we don't have diffusion anymore, and this is Anderson localization of a wave in general, okay? So now, was already seen. Okay, so this is what I just said. This was already seen, for example, in 3D scattering samples for acoustic waves. So people took a sample like this one, which is just composed of aluminum beds brazed together, and they have sent acoustic waves to this, and they have verified Anderson localization. Now, in this kind of system, it's a little more subtle to verify it, because since the sample is finite, you don't have a complete localization, but every time some of the wave is going to scatter, so you need to take a look at different observables in order to check that that the acoustic wave was localized in the Anderson way of localization. So one of the observables, for example, I have put here, is the statistics of the transmitted intensity. So when you measure the transmitted intensity away from the localized regime, you have a distribution of intensity. So what's the distribution of intensity? It's a probability of having a certain intensity as a function of the intensity. So this distribution follows a simple Rayleigh law, which is quite general for any kind of scattering, of wave scattering, light, any kind of wave scattering. And when I localize, I diverge from this. So this behavior diverges, and it's not a simple exponential anymore, but you have a decay which is slower. Okay, so this is one of the possible signatures of Anderson localization. Okay, that I should search for if I have a finite sample. People have verified this with atomic waves. So you all know after these 2 weeks that matter is a wave if you go to sufficiently low temperatures. And what we are seeing here is a condensate put inside a potential made by 2 light sheets that present speckles. So you have speckles here, speckles there, which makes a 3D speckled light potential. So this is a random potential for the atoms, and then the atoms scatter, the cold atoms scatter in this potential, and they get localized if you are in conditions for Anderson localization to occur. So you see here a condensate that stays with the same shape for over 6 seconds. Okay? So this is Anderson localization for matter. And light. And how about light? Can we also see Anderson localization of light? Light is also a wave, so I should see, right? But actually, people have never seen up to now, people have tried a lot, have still not seen Anderson localization of light. And we believe now, since results from 2014, that this is connected to the vectorial nature of light. So the fact that light is a vectorial wave would prevent Anderson localization of light. And why this is linked to the dense situation? Because the onset of 3D Anderson localization would have been exactly at the onset of the dense regime, when we begin to have more than 1 atom per cubic wavelength. So these things should happen at the same time, and it does not happen. It happens, we see theoretically that it happens if I make a model of scalar light. This means that I remove the transition probabilities as a function of polarization. I treat my atoms as 2-level systems, and in this way I can get back Anderson localization of light in theory, but in practice light is vectorial, and I don't get this in practice. I mean, I don't get this without applying magnetic fields. Then you have strategies that people are pursuing in order to see Anderson localization, 3D Anderson localization of light. Okay? So this is connected to the same fundamental problem. And this problem, light scattering in the dense regime, is a problem that we want to study in our laboratory. So we want to study with strontium. So I'm going to go maybe a little quicker on the strontium properties. But strontium is an alkaline earth atom, presents broad transitions between states with same spin, and present narrow transitions between states with different spin, because the light cannot exchange the spin of the electron. So these transitions are actually forbidden in first order, but they happen in next orders for several different reasons. So you have a narrow transition here, which is the red, which is nice for cooling, and you have ultra narrow transitions here of millihertz that are used for metrology. Both blue and red transitions are simple transitions, which is nice for studying light scattering by atoms. And so this is a nice atom to pick up to study these dense regime stories and etc. So in our laboratory, we have an experiment that most of you must have seen. I mean, most of you that are here presentially, not the people that are watching online. And actually what we have is atoms trapped in an optical dipolar trap at 1.5 microkelvin, and we have 5 times 10 to the 6 atoms there. And we think that we are maybe already dense enough to begin our studies, but we are still characterizing the sample because it's not easy to see a sample that small. So this sample makes 12 by 12 by 6 micrometers. So we are improving our imaging system and characterizing the sample, but soon I hope we'll begin to measure the transmission of light through this dense sample and verify this saturation of absorption, eventually try to verify the saturation of index of refraction, etc. Okay? So this is one of the experiments we have here. So now I pass to a second moment of this talk. We have discussed atoms interacting with light in free space. And now I want to to make atoms interact with light trapped inside a cavity. So trapped, it's not really a good word, but let's say light inside an optical cavity and the atom interacting with this light inside the cavity. Okay, so I would like to discuss this second situation, which is the situation of the second experiment we have in our laboratory. So first, why a cavity? So again, I'll try to be basic, maybe too basic. I'm sorry if it's too basic. But why we like cavities and why people put cavities and atoms to interact so much. So they have done this in the past and they still do this. Why is this the case? Okay, so first, a little information about light cavities. So I call a light cavity any physical system that can keep light turning in a recursive path for some time. Okay, so simplest way of doing this is doing a Fabry-Perot interferometer. So you put 2 mirrors, as I'm showing here, 2 mirrors. So these 2 mirrors, they are converging. So they determine a Gaussian mode of light. This is just a special mode of light that becomes itself after a round trip. So light goes converging here, diverging, then is focused back here, diverging, then is focused back. So you see that it comes back to itself after a round trip. So this is a stable mode inside your cavity. Okay? So from the spatial point of view, this is a stable mode. This is nice. And then this light is going to be, can be circling inside for a certain time, which is determined by the reflectivity of your mirrors. So the amount of time that your light keeps circling here is given by the finesse of your cavity, F. Okay? So the higher the finesse, the higher number of turns that the atom does, the light does in average before being lost. Okay, but this is from the spatial point of view, this mode here. Then from the spectral point of view, from the point of view of the frequency of light, not every frequency can be trapped, can be kept inside the cavity. Why? Because in order to have light kept in the cavity, light has to come back in the same mode, but also in the same phase. Because if light does not come back in the same phase, it's going to interfere destructively with light that was in the first path, and then this makes destructive interference between all those paths, and light is actually not inside. It becomes completely reflected. Okay? So so I just have specific frequencies that fulfill this constructive interference condition. And I show here a graphic that shows the transmission of the cavity as a function of the frequency, and we see that just for specific frequencies I see total transmission. And when I have total transmission, this means that I have light inside my cavity. So these frequencies here are exactly the frequencies for which each round trip makes a constructive interference with the other round trip, so I have constructive interferences of all those superposed paths. Okay? Okay, so this is a cavity. You have some characteristics here, but I'm not entering into the details. Something nice to tell maybe is that the intensity inside your cavity is equal roughly to the finesse times the intensity that you put you input. Because since you have lots of round trips, the intensity inside is much higher than outside. Okay, so maybe something to say. So this means that if I put an atom here to interact with my light, I will have lots of intensity. This can be nice maybe for some applications. Let's see now why this is nice. So if I put an atom inside the cavity, what's nice is that now, before I was having a quantum system, the atom, but the light was classical. I was not talking about quantization of light. Okay, I discussed a little quantization when I discussed the emission of photons, but these photons are emitted and they are lost. Now, if I put my cavity, I can have one quantum system, the atom, in interaction with another quantum system, which is the photons inside this light mode. So I have this stable light mode of my cavity, which is the resonator mode of my cavity. And then I can put here 1, 2, 3, 4 photons. I can treat, if the coupling between the atom and light is strong enough, I can see the effect of the quantization of this mode. I can see the effect of single photons inside this mode. This means that the cavity plus the atom configures two different quantum systems in interaction. So they are interacting, okay? So I can put a coupling here and I can make these two-level system interact with the state of this light mode, okay? Which can be at the 0 photon state, 1 photon state, 3 photon state, and etc., okay? Okay, so this system now, so I have a typical parameter, which is the coupling between the atom and the state with just one photon. So here I have parameters that you all know. Ni0 is the natural frequency of the transition, and this V is the volume of the typical volume of this mode here, okay? Well, and then you also have losses. So kappa is the loss from the cavity. This measures the fact that the light can escape. And gamma is the loss from the atom. Gamma, we all know, is the spontaneous emission of the atom. So if the coupling between both wins over the losses, this means that I am in a situation when I have this, I am in the strong coupling situation, so in the strong coupling regime. This means that the coupling between my atom and my one photon is stronger than the losses. This means that I can see a coherent behavior between these two quantum systems, okay? And this allows, for example, to directly verify the quantization of light. So this is a first experiment that saw the quantization of light. So here, what we're seeing in these first graphics here is just the oscillation between the excited population of your atom as a function of time, the time that the atom passes interacting with the light inside the cavity. Oh, I'm sorry. And when I do the Fourier transform of this, I see that I get different frequencies inside this oscillation. And these different frequencies are related to different number of photons inside the cavity, because actually the coupling between the atom and the photon state is dependent on the number of photons. So it depends as the square root of the number of photons. So when I do the Fourier transform, I see different discrete peaks which are related to the photon states. So I see clearly the existence of photons, okay? So this is nice. The cavity can put now two quantum systems in interaction. So this is a nice thing about the cavity. Okay. So so it's really nice if I am in the strong coupling regime, but I can be not in the strong coupling regime, but I can be maybe in the collective coupling regime when I need to have n atoms in order to see one photon. Or I can be in the regime where I need n atoms and I need n photons in order to see a coherent coupling, but still I have interesting physics here when I trap light to interact with my atoms. I'm going to show you something that we pursue in the lab. But in the lab, I don't have this simple cavity. We have in the lab a ring cavity. So it's a ring cavity is a cavity with 3 mirrors. Why do I put 3 mirrors? I put 3 mirrors because when I have, because with 3 mirrors, I can have light going in one direction and light going in in the opposite direction, and these two modes are different. So now I have atoms interacting not with only one mode, but the atoms interact with 2 modes. 2 light modes, one propagating and one counter-propagating, okay? Okay, so you can say, nice, so I don't have 2, I have 3 quantum systems possibly, okay, but what's about that? But apart from this, also in this system, the momentum of atoms become a relevant degree of freedom. Why is this so? Because if I absorb a photon from one propagating beam and I emit the photon in the counter-propagating beam, I absorb the momentum of the photon in the first absorption, and I have another kick in the same direction when I give the photon to the opposite direction. So this means that when I do this exchange of photons, take from one mode, give to the other, I receive two recoil momentum kicks. So this recoil momentum is the momentum of one photon. So I receive 2 of them. This means that I couple these events of redistribution of photons to momentum changes in my atoms. And if my atoms are cool enough, the momentum is also another degree of freedom, which is quantum, and all of this is coupled. And so you have several different ingredients here. So I'm just gonna show one experiment that was done in this kind of systems in the past. So in this experiment, people, so they have sent light in just one arm of the ring cavity. The other arm was empty, no light, and you had cold atoms here trapped in one arm here. Okay, so these atoms begin interacting with light, so they absorb light and they re-emit light either in the same mode or in the counter-propagating mode. This means that you begin having a little light in the counter-propagating mode. Okay, and so when you have light in the counter-propagating mode, the superposition between the propagating and the counter-propagating begin creating an optical lattice here, and which makes a potential for the atoms. So you begin to modulate the density of the atoms. This density modulation is a grating, and the light can be scattered in this grating with higher probability. So you begin to scatter more and more light, and at some point, what you get is your atoms are surfing kind of surfing in this wave. Okay, so you get a coupling between the momentum of the atoms and the momentum of the atoms and the power on these 2 arms. Okay, and if you go to a situation where you have, this is another experiment, another moment, and if you go to a situation where your cloud is cold enough, you can see that after this interaction, so when you begin this interaction, sending light just in one arm and see what happens on the other arm, you see exponential bursts of light, which is called the collective atomic recoil laser, because it's a laser mediated by the momentum of the atoms. And you also see that the momentum of atoms after this interaction is separated by unities of 2h bar k. Okay, so you see points here because you have interacted coherently with this light, and you have redistributed in a quantized way the momentum of your photons, of your atoms. Sorry. Okay, so this was done in the past, and here in the laboratory, what we want to do is to use this effect actually. So we put a ring cavity around atoms which are trapped. So we first trap atoms in a. Actually, this has changed a little. So we put atoms. Now we are doing the opposite way. So let me tell you the opposite way. We put atoms inside our cavity, and these atoms are going to be trapped already in a optical lattice made by the pump and the probe beam. So we send light in both. We will send light in both arms. So you have seen already Dalila explaining about the experiment, maybe. Dalila, I don't know if she's here, but she should be. No, but she explained to people last week about her experiment, and then and in her experiment. She traps atoms in this optical dipole trap. She wants to trap, and then these atoms this is in a vertical direction, and the atoms on this lattice are going to oscillate. This is a quantum effect called Bloch oscillations. The atoms that are cold enough, they oscillate in momentum space on this lattice. This oscillation is proportional to the force that we apply to these atoms. This means that this oscillation frequency is proportional to gravity. And the fact that these atoms are inside this ring cavity makes that this oscillation will be visible in the probe light. So we're going to see this oscillation on the power oscillation of your light. Okay? And so this is going to be a way of measuring gravity with your cold atoms. So this is another kind of thing that we do we want to do in our laboratory. So okay, I just show here quickly the team. So the big boss of the lab is Professor Philippe Courteil. I am the other principal researcher. And then we have 4 PhD students and a master student. I am 2 master students. The other one is Claudio, but he was not still here for the picture. So Claudio is here. Okay, he's beginning now. And with this, I would like to thank you for your attention. And yeah.
Thank you very much, Raul.
I think I don't have time for the next part, so I'll stop.
Now we have time for questions. Please.
Hello, Raul. Firstly, thank you for the very nice talk. I really appreciate it. And I would like to know about the Anderson effect, because I would like to know if it's possible to produce quantum memory using the Anderson effect of Anderson localization.
Well, I would say that maybe yes. I have not seen proposals in this direction. So quantum memory, for a quantum memory, you need to have something. So you need to be able to access it and to store, and then to write, to store, and to read. So I just give this general information. So of course, Anderson and also store in a coherent way. This means that it's not just keeping the energy of light there and then asking how many photons have I put, but you want to know how many photons and in which state. Even if they were in a superposition state, you want to recover this information. Okay, so this is important. Okay, so I have not seen proposals with Anderson localization. Maybe because when you talk about diffusion of light, I don't know if it's so easy to keep the coherence of this storage. Okay, so it's easier to couple to a mode coherently and then protect this mode and then recovering this somehow. I think this is an easier thing. So what I was going to say is that you can do this with atoms in a lattice, for example. So in a lattice, you know the superradiance and subradiant modes. And then you can, you could imagine exciting your atom in a your optical lattice in a superradiant mode. So you have these modes. So here you see as a function of the wave vector of light, the projection of the wave vector of the light in the plane should be quick. The gamma of the transition. So you see that you have lots of superradiant modes, and this dark blue here is lots of quite subradiant modes also. So you could put in a superradiant, make an operation to your atoms in order to make a superradiant mode become a subradiant, store, then come back. All of these made coherently. So you know at every step where you are, what you are doing. So I think this is needed for a quantum memory. So I never seen proposals in localization. I don't know if it's possible. I don't imagine a protocol in this direction. But
thank you. Another question. It's about, if I understand correctly, what is the effect of the natural line width on the super regions?
So the natural line width is the scaling parameter of everything. Let's say, if you have a cloud of atoms with the same, let's say, rubidium atoms or strontium atoms with same optical depth, the superradiant is going to scale with the optical depth and also with the natural line width. So as strontium for the blue transition has a line width which is 5 times higher than rubidium, you have a superradiant rate 5 times higher also because it scales with gamma.
All right. Thank you.
Okay.
Thank you. Do we have more questions? Vanderlei? Dalila, you have a question?
No, you arrived 1 hour later, actually. I thought it was going to be...
Okay, but you have 2 questions in the chat.
I mentioned you, but you're not here.
They note. Okay. by Alexandre Andrade. He have two questions. The first one, could you please comment a bit more on how to achieve such a dense cloud on atoms? If I understand it correctly, you would need a cloud with at least 10 to 20 atoms per meter cubic for a visible laser.
Yes, indeed, it's exactly this. So we talk about atoms per cubic centimeter, it's just a normal unity, but it's, okay, so 10 to the 14 per cubic centimeter or 10 to the 20 per cubic meter, this is correct. Densities in cold atom samples are not already that far from this. It's not that hard. But the main thing is that I think one of the main problems is that when you begin cooling down your sample, you begin scattering photons also, and this limits the maximum density that you can achieve. So we are trying, so we think we have maybe succeeded, but we don't have resolution to see. So one of the things we do is when we put atoms inside the optical dipole trap, we keep on the molasses beams. So we keep on molasses beams on all directions. There are challenges. One of the challenges is this scattering of light, and the other challenge is also the fact that the dipolar trap makes an makes a shift of your transition, which is a function of the position. But you can use it on your benefit. If you make, for example, a ramp, you can imagine making a ramp of the frequency, and so you go cooling down slowly and keeping the atoms lower and lower and lower with your molasses. So we are trying these kind of strategies. I don't say we have finished it, but you have proposals, you have people that tried similar things, so we are in this direction now.
Okay, they have other question by Alexandre too. He asked, I assume the level structure of the strontium plays a role in achieving the dense cloud. Could it be done with an alkaline such as rubidium or cesium?
I'm sorry, for the first part I missed.
I assume the level structure of the strontium plays a role in achieving the dense cloud.
No, I think I don't think the level structure is bad. This is what he means, right?
Yes, he wants to know if the cesium or other alkaline atoms will work.
No, so strontium is really nice because of the transitions, J equal to 0 to J equal to 1. All predictions are made for this, so this is good to have strontium. And I don't think it's a problem to have strontium. I think you can cool them down. The fact that strontium has a narrow transition is really nice because you can go lower in temperature without evaporative cooling, without losing atoms. So our cooling stages are rather efficient. No, I would not say it's a problem, strontium, compared to rubidium. Maybe there are other atoms that are even better, but I think strontium is quite good. After, strontium has problems for condensing. So for having Bose-Einstein condensate, people have done it, but due to so some isotopes have small scattering length, others have too big scattering length. So for condensing, because you need the collisions to thermalize, this is another story, but we don't need to condense, so it's not a problem. Okay, thank you.
Okay, thank you very much. Oh, you have more questions? Sorry. Oh no. Okay, thank you very much, Raul.
Thank you.